everybody, thanks for choosing this session. My name is Mike. I build distributed systems for fun and living. And today I'd like to talk about a fundamental law of building those systems, which obviously is the famous CAP theorem. The CAP theorem that is probably the most well known from its graphical representation as a triangle, where every edge of the triangle represents one of the three properties. So consistency, availability, and partition tolerance. And on top of that, we have this catchy wisdom saying that in any distributed shared data system, we can pick at most two at a time. And that's nice because the triangle makes CAP extremely easy to remember. In fact, when Eric Brewer was formulating his CAP conjecture around 1999, this is more or less how the things looked like. However, the triangle has as much CAP as cappuccino. So, okay, the letters may be fine, but we are missing a lot of important details here, the details that I would like to focus on today. Now, some of the people were trying to go one step further and improve the situation by putting the categories, particular categories that are a consequence of the three properties to the diagram, and trying to categorize the databases and the systems that they are using into those groups. So that's how we got the CP, CA, and AP systems. However, instead of making things better, it actually made things even worse. Because world is basically not that simple, as we will see later on today. Now, from time to time, we also observe the product announcements, like the one from last year from Amazon S3 team, that the products that previously were known from high availability and scalability can now offer something more than just eventual consistency. But what does it mean? How did they achieve that? Does it mean that AWS took all three CAP properties at the same time? Has the cloud changed the rules so much that the CAP theorem does not stand still today? Well, the answer is obviously no. So the CAP is not a random hypothesis that you can find on the internet. It's a proven theorem. We can even think about it as gravity for distributed systems, so a law that we have to obey no matter if we like it or not. But the true reason why we are talking about this and why the researchers were talking about the CAP theorem for such a long time was that CAP is also extremely misleading, and we will cover those misleading parts today. So what's left of CAP theorem after more than 20 years since it first have been formulated? Should we still care? Is it still relevant for the systems that we are building? What about the tools? What about the databases? What about message brokers? Everything that we build right now. How CAP affects that? Well, if you're curious about the answers, that's great news, because this session is exactly all about that. So we will go through CAP theorem, we'll go through the tools, focus on very practical aspects of the CAP theorem application for the next 40 minutes, I believe. At the very end, we will have a dedicated time slot for answering questions, so I'll do my best to do so. All right, I guess we can slowly start. And I believe the best way to start is to make a quick recap in order to make sure that we are on the same page in terms of CAP theorem understanding. So we started from a triangle. Let's go one by one through the properties that could be found there. And of course, probably the easiest one is availability, because it's the most intuitive one. So availability in terms of CAP theorem has been defined like this, that every request received by a non-failing node must result in a non-error response. What does it mean? So when the node is alive and the read operation comes in, this node has to reply with some data as a result of this read operation. And when the write operation comes in, this write has to be accepted. This is basically how availability has been defined for CAP theorem. Now, let's complicate things a little bit and introduce the concept of a network partition. So a network partition is a kind of communication issue, the network issue, which effectively splits the nodes within our distributed systems into groups, and those groups can no longer communicate to each other. So, like in this case, the nodes on the left side of the partition are not able to call those on the right side of the partition. However, both groups could still be reachable from the outside, can still be reachable, for example, from the internet, which means that effectively we could have read and write operations, competing read and write operations, probably even related to the same value happening on the both sides of the partition at the same time. And of course, the problem is that if we will allow all of them, then we potentially will have some problems, we will have some inconsistencies, we will have some conflicts, and somebody will have to do something with them. And this is, in fact, the essence of the CAP theorem. So CAP theorem is all about the decision making when the network partition occurs. So what are our options? So option one is basically to make sure that only one group of nodes will be available at a time. In this way, we can protect the consistency, so we can avoid inconsistencies, we can avoid conflicts by basically making the other side of the partition unavailable. Which one to choose? Which one to make available? Usually, we use the side which contains a majority of nodes. Why? The answer is fairly simple, because according to maths, we should have only one majority at a time. So that scenario is a typical example of a CP system, so a system that is consistent and partition tolerant but sacrifices availability. Alternatively, we could say we don't care. Just accept all the reads and writes on both sides and handle inconsistencies later, somehow. But of course, such an approach is risky in terms of data conflicts. But in terms of availability, it's exactly what CAP A property was about. So we are accepting all the reads and writes that are happening. So that's how we end up with an AP system, so available and partition tolerant. Now the things will go start a little bit more interesting. So what about the node failures? When we have two nodes, A and B, and A wants to call B for something, and B goes down, well, isn't it a kind of a network partition? It looks quite similar. Well, the answer is no, because the node failure is not a network partition, because the network partitions are about the network, about the connectivity, not about the node liveness. But failures and downtimes happen pretty frequently. In fact, even the most stable system will need to go down for some time for maintenance or whatever, or we will need to restart it from time to time. So wouldn't it make sense to introduce or cover such a concept in something as important as the CAP theorem? Additionally, partitions, unlike availability and consistency, are not something we choose. So the network partitions are basically happening. Those are inherent part of the networking of the distributed systems. But to make things even worse, if we have two nodes and the node A tries to do something with node B and the communication fails, it might happen that from A's perspective, it is impossible to say whether the reason for that was a network partition, timeout, or the failure of the whole node. And this is exactly why the CAP's theorem strategy of handling network partitions have consequences, practical consequences for situations when which are not directly covered by the CAP theorem, like the node failures. So let's jump to the last property, which is consistency. And in terms of consistency, for CAP theorem, it is defined as linearizability, also known as a strict consistency. And what does it mean? Well, what in linearizable system, all operations behave as if they were executed atomically on a single copy of a data. So in other words, our distributed system should act as a non-distributed one. So like everything is happening on a single node. As a consequence, in a linearizable system, it is impossible to observe a problem called a stale read, so a situation when after updating a value, the outdated one could be returned for any of the consecutive read operations. So as you can see, linearizability is really strong guarantee, and because it's so strong, it's also quite useful for us, for the people that are building distributed systems or using them. But what about the non-C systems? So what about those systems which do not provide linearizability? Does it mean that they don't provide consistency at all? And in fact, the answer is no, because consistency is a whole spectrum of different models and guarantees. And why we have so much choice? Well, the answer is very simple. So all those options represents different trade-offs between the performance and fault tolerance. If we'll take a look at the hierarchy of the consistency models, like here, we'll see that under linearizability, we have plenty of different weaker models, like read your writes, which basically means that if a node writes something and then wants to read the value that has been just updated, it should see its own read. We have also stronger consistency than this one, called a causal consistency, which basically means that we will preserve the cause and the relationship between the operations in terms of ordering. So as you can see, what we call eventual consistency is not the same as no consistency at all. But speaking about consistency, somebody has to ask me about the ACID. So what about ACID? How ACID fits into the CAP theorem? If we'll take a look one more time at the hierarchy of the consistency models, we will see that linearizability is on a completely separate subtree than the transaction isolation levels. So this suggests us that there is a slight difference between those two. And one of the reasons is that ACID is about transactions, while CAP theorem is about operations. What is the difference? So an operation is a single read or write, very simple thing. However, transaction is a logical group of the operations. So that's one of the main differences here. Additionally, the phrase consistency in ACID is not about linearizability, it's about the invariant. So about making sure that the transaction will move the database from one consistent state to another. And that's why we shouldn't confuse ACID with CAP. Of course, this is hard because the term consistency is extremely inconsistently used across the computer science, depending on the context. But the point here is, do not confuse ACID with CAP. Those are two completely different things. Now, we started from a triangle, and we should be able to finally rephrase the CAP theorem in a more practical way. So I would say that CAP theorem says, when a network partition occurs, your system has to decide whether to sacrifice availability or consistency, understood as linearizability. This is the essence of the CAP theorem. Now, let's jump to AWS S3, so a service that I mentioned at the very beginning of the talk. For those who may not know what S3 is, you can think about it as a cloud-based hash table for binary data, for blobs, so a key value storage for binary data. And those binary data are represented as objects that are grouped into so-called buckets. And the nice thing about the S3 design is that all the data you are putting into it is redundant by default. So it means every piece of data will be replicated across multiple availability zones, which every of each has a separate power supply, separate fiber connection, and things like that. So our data is really secure by design. However, before 2020, the S3 was known from being eventually consistent. So it was a completely normal thing that after putting an object into the bucket, it was not immediately visible. So the changes being done to the objects were not immediately visible. However, the things have changed at the very end of 2020 when the S3 team announced something called here on the blog a strong consistency. And when I saw the strong consistency, it immediately made me think, How much cap does it have now? What this strong consistency means? Is it the same as linearizability? How much we can get from using the S3. So in order to find out that, I jumped into the documentation, and this is what I found. So first of all, in the chapter related to the data consistency model, this strong consistency has been rephrased to strong read after write consistency for puts and deletes. Which rather suggests that we have here at least the read-on-write semantics, but not necessarily the linearizability. Then, if we'll jump to the next part, we will see that the S3 for the concurrent simultaneous requests will prefer the latest one. So the latest timestamp wins is the strategy of handling potential conflicts coming from concurrency. But the bucket configuration itself is still eventually consistent. So it means that we have kind of a hybrid here, where some parts of the system provides stronger consistency guarantees than another. And of course, there were numerous attempts to try to put some light into how S3 works, including this blog post from Werner Vogels, which called the approach that S3 took as a smart implementation of a cache coherence protocol. But the truth is that it's still unclear. So we don't know whether this is a linearizability or something else, but it still feels quite strong. So at least from the user's perspective, this is exactly what users wanted. This is exactly what was expected for many, many years. And we have to probably accept the fact that we won't know how it works under the hood for sure, because as in life, the magician usually does not reveal its secrets, unless it's Google. And speaking about the secrets and speaking about squeezing a lot from the cap theorem, I must say a few words about Google Spanner. The Spanner is a highly available SQL database, a relational database running in the cloud. And it has been described in multiple papers, including this one, my favorite one, so-called Spanner, True Time, and the Cap Theorem. And the important and the interesting thing about this paper is his author. So the author of this paper is Eric Brewer, so the same person who initially created the cap congestion. That's why we should assume that this person knows what he's talking about. If we'll jump into the details of this paper, we will see that a spanner is technically a CP system, but also effectively CA. What does it even mean? How is it possible that with the cap theorem in place, a system could be almost categorized in two different ways? Well, one answer for that could be that if you're rich, the rules apply a little less to you. And of course, the big enterprises like Google are excellent in throwing more money into the problems. But of course, it's not only this one, because Google has years of experience in SRE and building reliable networks, so they are able to mitigate some of them, the common issues. But still, being rich, being experienced is not enough. You also have to be quite clever about what you're doing. And Spanner is full of really smart solutions. So first of all, to achieve the same consistency and isolation guarantees as we know from relational databases, Spanner uses two-phase commits with strict two-phase locking. So the approach that is known for years, but it's also known from not scaling well. It's the fact that some time ago, the two-phase commit has been even called an anti-scalability protocol because, for example, a requirement that all of the participants of the two-phase commit have to be up and running for the whole time. And that's where the clever part kicks in. So Spanner combines the two-phase commit with Paxos, with distributed consensus algorithm, in order to mitigate the availability issues and effectively get us the best from both worlds. But a true magic comes from true time, so a solution that acts like a global synchronized clock. And this is extremely interesting because, as we know in distributed systems, we often cannot rely about the clock values. So even with solution like network time protocol in place, the clocks may still diverge, may still drift. And true time does not change that. So it still accepts the fact that clocks are imperfect, but tries to improve them. And of course, part of that is using the GPS receivers and atomic clocks on the hardware side. But the true magic comes in how the true time handles time on the software side. And despite like the standard approach, the true time timestamp is not a single value, is a group of values. Those are two values that create a range. So we have an earliest and latest timestamp. And the true time guarantees us that the actual clock's time, the real one, will be somewhere in between those two. But of course, this will be quite useless without the promise that the delta between those two is very, very small and it's predictable. And this is the case for true time. Now, why is that so useful? Let's imagine we have two operations or two transactions and they are corresponding true time timestamps. If we know that for two operations or two timestamp, there is no overlap in those ranges, we know for sure that there is an absolute order of those operations, so one happened after another. However, if we will have two true time timestamps, which ranges do overlap, we cannot know for sure which one happened as the first one, which was the second. So what the spanner does under the hood is basically it applies a small delay that is related to the maximum error of the true time timestamp to one of those transactions in order to make sure that the order is known. So as you can see, this is a way to achieve the linearizability, so introduce the global order of operations thanks to true time. Now, there was also mentioned that the true time is effectively a CA system. So we know that consistency is always guaranteed because of the two-phase commit. What about the availability? If we'll take a look at the SLA of spanner service, we will see that it guarantees so-called 5 nines of availability, which effectively means that the whole service could be down for 5 minutes and 15 seconds per year, which was pretty impressive, but of course it's not the same as being available for the whole time, like the CAP Theorem says. But in fact, Google claims that effective availability is even higher thanks to the effect called differential availability. So differential availability says that if we are using an external system and the system is down, the only way for us to know that the system is down is to try to use the unavailable part at the exact moment when it's not available. In other words, it is probable that our application won't need spanner when it will be down for a moment. So that's how effectively the availability of the service would be even higher. So we can say that it's not a crime if you don't get caught. And as you can see, spanner squeezes really a lot out of CAP Theorem. So it's very, very close to get all three at the time, but of course it's impossible to do so. And since we've jumped into the SLA of spanner to better understand what it provides in terms of CAP Theorem, we can do the same for S3. And if we'll take a look, instead of the 5 nines, we will see only 3 nines of availability. And this is like the default expected availability for the S3. However, unlike spanner, this availability could go down, and it's explicit here. What will happen if the availability of S3 will be less than 3 nines? Well, we'll just get a discount, nothing else. So according to the SLA, there won't be no discount even if the S3 will be down for 1 minute and 26 seconds per day, which is of course a lot more than for spanner. And surprise, surprise, it is not enough to call it available system from the CAP Theorem point of view. But the consequence of all of this is that from my point of view, the SLA is the new cap. So those 10 or 20 years ago, the cap theorem was really useful for categorizing the system, for trying to express what the system provides. But now the SLA is the most important stuff, because this is what your customer will pay for. This is what we expect. This is what we can demand, because it's a matter of guarantee for us. And effectively, cap guarantees are being hidden under the availability guarantees. So availability, but why availability? What is so special about that? And if we'll think for a moment, it will turn out that availability issues are the easiest to recover from. So if we are building a system that uses an external service like S3, we should be already prepared that the external system will go down, will be unavailable for any reason, which means that even if the service provider will lower the availability a bit, our application should not need any changes. However, if the same would happen to consistency, so if we would have an unpredictable consistency, this would probably be a disaster, because we couldn't rely on our application at all. So availability becomes a rug to sweep under all the issues and all the trade-offs from the service provider side. But does it mean that the cap theorem is only relevant for those who are building databases or those who are service providers? In order to answer that, I would like to jump into another tool, which is Apache Cassandra. And for those who may not know, Cassandra is a database which we could summarize as a partitioned row store, which has been designed to be always readable. So the initial idea behind Cassandra was to cover cases like the network partition and make sure that all the nodes could be readable and readable for the whole time, no matter what happens. So that's why Cassandra was, for many, many years, a classical example of an AP system, so available and partition tolerant, but not really consistent. So because of the possibility of conflicts, there has to be a conflict resolution strategy in place, and Cassandra decides to accept the last write, so the write with the highest timestamp, as the latest value. Now, in terms of the design, we don't have a dedicated primary and secondary nodes. All nodes are equal, and they use a gossiping protocol for propagating the change across the cluster. So they work in a very similar way, like viruses like COVID-19 are spreading through the population. But a true reason why we are talking about the Cassandra today is its feature called tunable consistency. And tunable consistency, in essence, allows us to decide how many nodes from our cluster should take part in a read or write operation. So when we are performing read or write operation, we can say we would like to use only one node, two nodes, three nodes, majority of nodes, quorum of nodes, or all the nodes. And what's the point of doing so? Well, depending on the configuration, we will get a bit different consistency guarantees. So let's imagine that we have 5 nodes in the cluster, and we first wrote the value, the current value, the most recent one, into only one node. Then if we will use 3 nodes for reading, it might happen that those 3 nodes don't have the latest value yet. So that's why in such a setup, we will have rather an eventual consistency, because it may happen that the latest value won't be returned. However, if we will increase the number of nodes we are writing into to make sure that in every case, the set of nodes used for reading will overlap with the nodes used for writing, then we will know for sure that the latest value should be found. And thanks to the conflict resolution strategy on the read level, this latest value should be returned to the client. So instead of eventual consistency, here we will have something more like a consistent and partition tolerant system. But the real point here is that for some of the tools, we can make different availability versus consistency choices per operation. So it's no more a kind of classification. So we cannot classify Cassandra and say that it's always an AP system. It all depends also from how we are using it. But in terms of flexibility, this is not all what Cassandra can offer. We have also something which is called a lightweight transaction, and the lightweight transaction mechanism uses Paxos under the hood in order to provide the linearizability for some compare and set operations. So those are the operations like insert if not exist or delete if exist. However, those lightweight transactions are known from being quite tricky and also to suffer from performance issues. So as you can see, the flexibility, this kind of flexibility does not come for free. So somebody will have to pay the price, either in terms of performance or implementation effort or anything else. But the true point here is that CAP affects both the database, the design of the database, and its users. So the users have to understand the trade-offs and have to know what they are doing. Now, speaking about the flexible data stores, flexible shared data systems, yet another example that I would like to bring is Apache Kafka. And this could be quite surprising for some of you because Kafka is not technically a database, but still it fits into the CAP theorem really, really well. So for those who may not know what Kafka is, we could simplify and say that it's a distributed append-only data log. And of course, this is huge simplification because right now the Kafka is a lot more, it's a whole ecosystem with a huge community, but in its core, it's a distributed append-only data log. And in fact, for the purpose of today's session, this is more than enough to try to understand how Kafka works. One important design decision that is reflected in many choices that we'll see today is that Kafka has been built for scalability. And that's why the messages within Kafka, so the messages within log, are basically grouped into so-called topics, and each topic is consists of multiple partitions, or could consist of multiple partitions. So we can think about the Kafka topic as a log of logs, where the lowest level of log is a Kafka topic partition. And now, why it's so important for scalability? Because the ordering guarantees, so the preserving the insertion order of the messages is guaranteed only on the partition level. So the messages across different partitions or from different topics do not have any correlation in terms of the ordering. How to ensure that? How to make sure that we are consistent in this case? Unlike with Cassandra, in Kafka, we have designated leader node and we have followers. How does it look like in practice? So every topic partition may have one or more replica, but only one at a time could be a leader. And the leader replica has a very special role to play. So first of all the writes, so all the messages being produced from the producers have to go through the leader of a certain partition. So that's how Kafka makes sure that the insertion order is being preserved. However, and this could be quite surprising for some of you if you are using Kafka. Also, the reads come through from the leader. So leader has to handle both the writes and the reads. So what about the rest of the replicas that we have? The answer is very simple. They are being used for reliability purposes. And in order to catch up with what happens on the leader, they behave really similar to a standard consumer. So the replication is basically consuming from a leader. And because the consumers are polling for data, so this is how the data flow in Kafka looks like, the followers may lag. So it may take some time before the follower will catch up with all the changes that happened on the leader side. Now, based on this lag, so based on this, this time that we are lagging behind the leader, we will have two types of replicas. So some of the replicas will be called an in-sync replicas, which means they are not lagging too much, they are quite fresh. But those who are lagging due to, I don't know, networking issues or performance issues will be called out-of-sync replicas. What is the difference? What is so special about the in-sync replicas? Well, if the leader node will go down, the in-sync replica, only the in-sync replica by default, may become a new leader. And speaking about the leader, when we are writing new messages, we are adding new messages to Kafka. As I mentioned before, they have to go through the leader. So the leader gets those new messages, but the write is not considered complete from a leader perspective, as long as the message is not being fully propagated across all the in-sync replicas. So to make sure that this does not violate the consistency, the leader makes those messages not readable. So it means that if we wrote something to Kafka, it might take some time before the read operation from the same partition will actually see those data. So does it mean that there is no read your write semantics? So does it mean that the consistency guarantees in Kafka are so weak that even the read your writes is impossible? Well, it all depends on the configuration, again. So that's one of the reasons why Kafka introduced a concept of a producer ACK, so acknowledgement. So when a producer wants to write a message, it could decide for how many in-sync replicas to wait. And of course, we can wait for nobody, so have a fire and forget semantics. We could decide to wait only for the leader, or we can say we would like to wait for all the in-sync replica before considering the write as done. And with the last one, we will effectively get the read-on-write semantics. Why do we have this property? So of course, it's again a trade-off between the performance measured in producer's wait time and the durability of messages. Now, speaking about the durability, what will happen if the leader goes down? And what if it goes down in the middle of replicating stuff? So let's imagine that we have those two messages that are not yet fully replicated, and the leader goes down. There's no node failure or whatever else. Well, as I said before, one of the in-sync replicas will be elected as a new leader, but the messages that have not been replicated to this new leader may effectively be lost. So in fact, consistency does not guarantee durability, and this is a common misconception not only related to CAP Theorem. Those are just two completely different things, and while durability is extremely important, it's basically something else. Now, with Kafka, I've said how to tune the consistency, but we can also make some changes to improve the availability. Why to improve that? Because right now we have only one leader that is responsible for reads and writes. So if it will become unavailable due to network partition or whatever else, it might happen that we effectively losing the availability. So what we could do? One thing is a solution called the unclear leader election, which allows us to elect a new leader from an out-of-sync replica if there is no in-sync replica in place. This is disabled by default, but why? Well, the consequences are in terms of durability. So if the leader had messages that have not been yet replicated to those out-of-sync replicas, such a newly elected unclean leader will basically be losing those messages. So we will lose some messages in favor of availability. An additional thing that we could do is to enable a feature called the follower fetching, which basically will enable us to perform the reads also from the followers. Not only from the leader. And this is quite tempting because it sounds really, really good. And you may even ask why it's not enabled by default. And in fact, the reason for that is that the follower that we will use may get the message, but it won't be fully propagated, and in the middle of the propagation, the leader will go down. So in fact, in this case, with follower fetching enabled, we can read a message that after selecting a new leader will not be available anymore. So that's clearly something that impacts the consistency, but also has a huge, could bring a huge boost in terms of performance, especially in a cross data center deployments. And of course, there is more than that. There are flashes, so the way how we are flashing changes to the hard drives. There are transactions, so transactional write semantics. There's a lot of different things, there are a lot of different configuration that could help us to tune the Kafka as we want. So as you can see, the configuration parameters basically define the cap trade-offs. And this should also be a proof that simple CA/CP/AP classification of the system doesn't make much sense, because it all depends not only how from how the system has been designed, but also how we are using it and what are the configuration properties that we provided. And that's how we've jumped to the end of my presentation. Now let's do a quick summary of the most important points. So first of all, the cap theorem is not going to retire. So it was with us for more than 20 years already, and it will be for next 20 or even more. And also another thing that I mentioned is that the consistency and availability are spectrums. So those are not just binary properties. You cannot be consistent or inconsistent, but in terms of cap theorem, both of them have been defined really precisely. So it's more binary than that. So the C in cap theorem means linearizability. So acting, where our distributed system is basically acting as a non-distributed one in a way, while availability is about being always available when there are no node failures. Now, the high availability, so something we aim for in majority of systems, is probably not enough to fulfill the cap theorem's availability criteria. But also the eventual consistency. So this thing that we can get from the non-C systems is a spectrum too. So we have weaker guarantees like read-on writes or causal consistency that could be more than enough for our applications. Also, the partition handling strategy matters. So despite the fact that network partitions are a really specific problem, the way of handling them has influence for many other issues, including the most popular ones like downtimes and failures. Now, in terms of the software as a service products, the SLA effectively beats cap. So we generally don't care about the cap properties. So we only care about the SLA. We see what is guaranteed to us. So make sure to read the fine print carefully before selecting your cloud-based service. Now, availability trade-offs are the easiest to be done on both sides, so on the service provider and the user, but consistency must be predictable for the whole time. However, in many tools, not all the operations will have to choose the same in terms of consistency versus availability, which means classifications like that you can find on the internet basically wrong. Also, the cap theorem is not only for database designers, because so much depends on the configuration. But also, as I mentioned before, cap focuses only on three things, so consistency, availability, and partition tolerance, but misses a lot of important topics like durability, latency, and performance. In terms of tools that we are using, like databases, they can be more flexible than we think. But the devil, as always, is in the details, in the configuration, the implementation. So know your tools, read the docs, make sure that you understand what you're doing. Now, if you look for some articles that can cover this topic a little bit deeper, here's a list of things that I've personally used for preparing for this presentation. And as the last one, you can find my blog post that's basically described my point about SLA being the new cap. And that's all from my side. Feel free to visit my blog or follow me on Twitter if you enjoyed my presentation. Thank you very much for attendance. And now we should have a few minutes to answer your questions, if any. Thank you. Oh, wait a second. Now it should be better. Yes, it's there. And let's take a look if we have some questions. So I'm really glad that you've enjoyed my talk. But if you have any questions, we have 4 minutes left.
Clemens Guggenberger here. I have a question. When you mentioned the true time trick to avoid consistency problems, you said to avoid overlapping timeframes, a small delay is added. I don't really get how that works or how that would work. Could you elaborate a little bit on that?
Yeah, so first of all, I would really recommend to go to the sub-true time and the cap Theorem paper. It's just a seven pages of A4 paper, but it's extremely easy to read and it's extremely interesting. But trying to answer your question, well, basically, as far as I understood, the spanner internally detects the transactions, for example, that have the conflicting timestamps, and for those decide to postpone one of them to make sure that the timestamps do not overlap.
So this is actually introducing an artificial ordering. It kind of like chooses by whatever the end timestamp is latest or something like that.
Yeah, and that's a good point. So it is artificial, of course, but we can say that in any system it will be quite artificial.
Yeah,
so how much the users will know if their timestamp is the true one, right?
Right, of course, yeah.
But yeah, that's really impressive trick. Basically, I was completely amazed when I first saw it.
Yeah. Okay, thanks.
We have a question. Is cap a property to be taken by developers themselves when writing applications or only when using third-party services? Well, excellent point. The cap theorem says that those rules apply to any distributed shared data system. So the first question should be whether you have one. But I would say that in any distributed system, so any system that uses network communication and contains of multiple nodes, being aware of those rules actually matters. So you will run into situations when you will question consistency. You will ask yourself, what can you rely in terms, or what can you expect in terms of consistency, or how much availability it will have. So those are normal questions. And probably from the practical point of view, you will focus even more on consistency part rather than availability. But still, all those things matter. Also, one of the most important points from the cap theorem that I personally believe is affecting the systems that we are designing are the network partitions. So a lot of people, at least from my experience, are basically ignoring the fact that the network partitions are somewhere there. And because of the property that I mentioned, that they are so hard to distinguish from an ordinary failures or network issues, every system that you will build will have to deal with such a case in some way. So for example, you will have a leader election process in place because you would like to perform a certain task only by one node. What you will do to avoid a split brain situation when under the network partition, there will be two leaders, or there will be a problem with electing a leader at all. So those are really practical things. So I would say yes, the CAP theorem basically is important for developers, but it all depends, of course, of what they are doing. All right, any more questions? We have one. What helps to decide which database technology to choose? Key value versus column base versus relational database versus document. Actually, we want to cache data like device serial number, prepared header data to show in UI, and detailed data for further processing. Well, that's an excellent question, but it's also an excellent topic for a separate session, because it would be extremely hard to fit it into a few sentences, but let me try. So one thing especially important is basically addressing the data model itself. So thinking about how the relations between the data look like. Are there more like contains relationship, like parent and the children does not have sense without the parent, then for example, a document data model may be nice. Or if you have a highly related model consisting of multiple entities, which basically fits well better into the relational model. And of course, there are other aspects like consistency guarantees, like performance characteristics that you all have to take into account. So it's a huge topic on its own. I'm afraid that I'm not able to provide you a better answer that quickly. But if you want, we can discuss those things, for example, on Twitter. Yeah, let me post the link to my blog, no problem. So as far as I know, the presentation also should be available soon somewhere. But yeah, if not, I will make sure that it's there. So here's my blog that summarizes the topic. Oh, it's available. Okay, awesome. So I guess we're running out of time. So thank you very much for all the questions, for your attendance, and yeah, enjoy the rest of the JCon. Bye.